Hello, students, subscribers, viewers, and future engineers. Here is the solution to problems 9 and 10 given in the final exams in December 2003 as two problems in the final exams in structural theory. By three-moment equations, determine the vertical reaction at B. EI is constant, so just the vertical reaction at B. So we write three-moment equations on spans ABC. ABC, there's no support movements or settlements. The moment at A, because this is the end and it is a pin, it's 0. The moment at D is also 0. So for ABC, 0 moment at A plus 2 times MB quantity 6, since EI is constant. So 6 over 1, or simply 6, span AB plus span BC 5 plus moment at C times span BC 5 plus 6 area 1A over L1, which is PA over L, quantity L square minus A square. So P36A is 2 all over L6, quantity 6 square minus 2 square. Then the value is 384. While for the 6 area 2B over L2, for this span BC, it is entirely loaded with this uniform load, WL cube over 4. So 36, 5 cube over 4, and it is 1125. Simplifying, 11 times 2 is 22 MB plus 5 MC equals negative 1509. So call this equation 1. Then we apply three-moment equation on BCD. There are only two unknowns, moments at B and moments at C. Moments at B and C. So MB times span BC, which is 5, plus 2 times M sub C, quantity 5 plus 4. 5 plus 4. Moment at D, 0. So that's why you have 0 here. 6 area 1A over L1 for this loading is the same as 6 area 2B over L2. We already calculated that. 36 5 cube over 4, while 6 area 2B over L2 is 8 over 60 because the centroid is farther from D, while if it is closer, 7 over 60 WL cubed. So 8 over 60 WL cubed. L is 4 and W is 36 equals 0. This is 307.2. This is 1125. Combining, transpose to the right, simplifying 5 MB plus 18 M sub C equals negative 142.2. Equation 2. Solving equations 1 and 2 simultaneously, we obtain MB negative 53.911 kilonewton meter and M sub C negative 64.591 kilonewton meter. Since all these are negative, so it means clockwise in BA and counterclockwise in BC. So the moment at B is moment BC, clockwise positive, so that's why it is applied as counterclockwise as shown. Same is true with moment at C, clockwise CB and counterclockwise in CD. So we can now compute RB left, considering AB summation of moment about A equals 0, assuming RB left and RB right are upward. So RB left times 6 equals 53.911 plus 36 times 2. So that's the equation. So RB left is 20.985 positive, so it is upward. Considering BC, summation moments about C equals 0, RB right times 5 plus 64.591 equals 53.911 plus the moment of the uniform load 36 times 5 times 2.5. Solving for RB right, 87.864 positive, so it is also upward. Therefore, R sub B is RB left plus RB right. So adding these two values, we obtain 108.849 kilonewtons. So upward. That's the answer to that problem. Problem 10, by slope deflection equations, determine the reactions at support C and D. E is constant. So at C, it's thus the vertical reaction, while at D, we have vertical reaction and moment reaction. MD. So by slope deflection equation, we know that the moment BA is positive 20 times 2, but the moment BC is negative 20 times 2, so it is negative 40 MBC. We then set up uh, slope deflection equation for BC. B is an interior support, C is also an interior support, so 2EI over L, quantity 2 theta B, 2 theta near plus theta far, minus 3 times delta over L, plus fixed end moment near, which is moment at B, which is negative because it is in the left. So MBC, which is negative 40, equals 2 EI. EI is, because I is 1.2 of I, then we'll just make it 1.2, assuming EI is 1. All over L, which is 4, then quantity 2 theta near, so 2 theta B, plus theta far, so theta C, minus 3 delta over L. There's no delta because there are no support settlements. The supports remain horizontal as shown, or the beam remains horizontal as shown. Plus fixed moment at B, which is at the left part of BC, so the fixed moment at B is negative, WL square over 12. So negative 34 square over 12. Simplifying this equation, so it is 2 theta B plus theta C equals 0. So that means this is uh, negative 40 also, so we can cancel. So zeros, 4 times 0 divided by 2.40. So that's why we simplify this equation into that equation. Call that equation A. Then for portion CD, because the load is not occupying the entire span, we have to evaluate the fixed moment by integration. So I'll have this strip W, intensity, thickness dx. So W as to x, this is x, equals 45 as to 6. So W is 7.5 of x. So MCB to EI again, because the far end D has expected moment. So 2 EI, 2 times EI. By the way, MCB is, we have to set up 2 times I, 1.2 I again, all over 4 quantity theta B, theta far, B is the far end here, plus 2 times theta near, the near end is C, then minus 3 times 0 because there's no settlement, then the fixed moment at C is positive, it is in the right part, WL square over 12, so 34 square over 12. Simplifying, MCB is zero point 0.6 of theta B plus 1.2 of theta C plus 40. Call that equation 1. Then MCD, 2EI, 2 times 1, I is 1 here, over 8, the span is 8. Quantity 2 theta C plus theta D, because D is fixed, no rotation, so it is 0. Then minus 3 times delta over L, 0 also, there's no settlement. Then fixed moment at C is negative integral of differential P. Imagine this is the concentrated load. Differential P W dx, so W is 7.5x. Then dx times quantity A, the distance of the strip from the left, which is 2 plus x. Then the square of the distance of the strip from the right, which is B, and that is 6 minus x, quantity square over 8 square. And the limits of x is from 0 to 6. 0 to 6. So simplifying, we have 0.5 theta C. The value of the integral is negative 891 over 16. Call that equation 2. Then MDC, it is theta D, which is 0, that is doubled. So half of the coefficient this time, half of 0.5 is 0.25 C. Then the fixed moment at D is positive. It is in the right part of the segment CD. And integral, same, you just copy this integral here, you just interchange the squared quantity. So this time 2 plus x is squared, then 6 minus x raised to 1, same limits, same the rest. So simplifying, MDC is 0.25 theta C plus 1809 over 16. And We'll call that equation 3. Equation 3. Then we apply equilibrium at C, MCB plus MCD equals 0. MCB is zero point 0.6 theta B plus 1.2 theta C plus 40. Then MCD zero point 0.5 theta C minus 891 over 16. So combining 0.6 theta B, then 1.2 plus zero point 0.5 of theta C, 1.7 theta C. Then this is positive to the right equals 891 over 16, then minus 40. And it is 251 over 16. Call that equation B. Solving equations A, this one, and B simultaneously, we obtain theta B negative 1255 over 224 EI, and theta C is 1255 over 112 EI. Therefore, moment at C, which is moment CD, is substitute here 0.5 of theta C minus 891 over 16, and in decimal it is negative 50.085 kilonewton meter. MD on the other hand is the negative of MDC, because MDC is expected positive, so moment at D is the negative of MDC. Then it is negative of quantity MDC 0.25 of theta C plus 1809 over 16. So calculating, moment at D is negative 115.864 kilonewton meter. So that's the answer here. Then we compute RC by first computing RC left, considering ABC. Summation moment B equals 0, RC left times 4 plus 20 times 2, RC left times 4 plus 20 times 2 equals 50.085. This, by the way, the moment at C is negative, so clockwise at the left, counterclockwise at the right. Moment at C is, remember, moment CD, that's why this is counterclockwise. Because for positive moment at C, it should be clockwise from sign convention or from our guide, Smiley. So equals 50.085 plus the moment of this load 30 times 4 times 2. So RC left is 62.521 kilonewtons upward. Then considering CD, summation moment about D equals 0, RC right times 8 plus 115.864 equals 50.085 plus moment of the load 1/2 of 6 times 45 moment arm 2. So RC right is 25.528 kilonewtons also upward. Therefore, R sub C is 62.525 plus 25.528, both upward. So adding, R sub C is 88.049 kilonewtons. So it is now RD that is left. So considering CD again, summation moment C equals 0, RD times 8 plus 50.085 equals 115.864 plus the moment of the load 1/2 of 6 times 45, 4 plus 2, so the moment arm is 6. Computing for RD is 109.472 kilonewtons. So that's it for this video.